associative mapping and the direct mapping. So today one more time, like I will revise the concepts: direct mapping and associative mapping and set associative mapping. Okay. So I was bit hurry yesterday, so I explained, like I gave only the brief about those concepts. So like today I'll clarify all the doubts. Like few of the students messaged me yesterday like that they have some queries regarding this mapping and associative mapping and the direct mapping. Okay, mapping process, associative, set associative, and the direct mapping process. Okay, so basically the mapping process is takes place between the main memory and the cache memory, and the cache memory will have only the information in the form of words. Okay, so it will store all the information in the form of the words, and whenever the main memory is going to fetch the data when it is executing the program, so it will like fetch the information in the form of the words from the cache memory. Fine. So I have one diagram here. So these are the different mapping techniques: associative and the direct mapping, and the set associative mapping we can call. Instead of calling self, the set associative mapping technique. Okay, as we know, this is a cache memory which is having 32K size and the 12 bits length, and each and every data is of 12 bits data. And the cache memory, and one more, we have 512 size and with 12 bits of the data length. Okay, and which is placed in between the CPU and the main memory. Fine. So the three mapping techniques I am going to explain from one of the source. So here, are you able to see the screen?
Yes, sir.
Yeah. So now, like I have one example. So the PPTs you can use for understanding this example. So here it is. I'll share the URL also with you people. Okay, just try to follow the concept. The thing is, we are going to move the data from the main memory to the cache memory and cache memory to the processor. So here and there, like we are going to move the data. Suppose, so we have some doubt, like you people have some doubts. Okay, so how many bits of data it is taking and all. So I'll clarify all those doubts. So we can call a line in the main memory which is responsible for moving the data. If a line is like it may be of the some address, typical address either 255, 256, 257 or 0 or 123, anything we can call it as one line, one particular line which is there in the main memory. Okay, for example, if a line is having the 16 bit size, 16 bit of size. Okay, if a line is having 16 bits in size, and suppose if we have 2 power 12, that means 4K bytes within the cache. Okay, 4K bytes within the cache, and which is having 2 power 8 bytes, that is 256. These all are the numbers which we are using. Okay, so 4K, if we are considering cache, 4K byte cache, then it will have 2 power 12, 12 bits of the data. I told you 12 bits of data we are using. Okay, so 512 into 12, like that. Okay, so here 2 power 12 is a 4K byte of the cache it is representing. Then 2 power 8 is equals to 256. We know this one. So 16 bytes, 16 lines you will have in this. 16 bytes or 16 lines you will have in this. Okay, if you are taking 2 power 24, then we are calling it as a 16M byte main memory. Okay, so just this is to specify different sizes of the cache. If you have 4K byte, then we are calling 12 bits. If you are having 8, then we are 2 power 8, then we are calling it as a 16 byte. Okay, if you are having 2 power 24, we are calling it as a 16M byte. That is in the main memory we are having, and which is cache is of 2 power 12. That means 4K cache, and the main memory is having 2 power 24. That means 16M. Okay, these are the two different sizes we are having. Main memory is of size 16 bytes and the cache memory is of size 4K, and the main memory will have the 24 lines, and whereas in case of the cache memory will have the 12 lines. That means doubling. So it is having the double size. Fine, it is having 12 lines, and here we are having the 24 lines, 2 power 24, 16M, that way. See, these are the general memories which we are using now. Okay, so try to understand the mapping concepts. There are three mapping techniques we have. Okay, so as per my example, I am having caches of 0 to 127, so that is 128 lines. We know how to calculate it, 2 power 7. Okay, which will give the 128 lines. And again we know I am making use of the 16 words, so 16 words I am using, so 2 power 4 it will give. One is 7 and one is 4. Okay, so 7 is what? Here 7 is the lines, number of lines which we are using, and 4 is what? The number of words which we are using. Okay, and suppose the memory is having 16-bit address, then obviously 2 power 16, that will be 65536, which is round off to 64 kilobytes. Okay, so that 64k words we are using in the main memory. So 64k is in the main memory. Fine. So the cache lines are in between 0 to 127. It is overall to 128 lines. Okay, and the main memory lines are 0 to 127 and starting from 128 to 255. That means together we are having how many? So together we are having how many? How many lines you will have? 2 power 16 lines you will have in the main memory. So 65536, like that you will have. So these are the memory specifications I am using in my example. So when we are going with the direct mapping, so the direct mapping is try to follow the concept. Okay, so direct mapping. So in this direct mapping technique, main memory lines whatever we are taking and which will be mapped onto the cache memory. Okay, which will be mapped onto the cache memory, and we will take main memory. For example, if it is a j and the cache lines we are considering it as a I, so j mod I we will perform when we are doing the direct mapping. So j mod I, suppose main memory lines are j and the cache memory lines are I, so j mod I we will perform. So instead of making it complex, so I'll tell you one simple example. Just try to follow it. When we are making use of the direct mapping technique, okay, when we are making use of direct mapping technique, 16 words are divided into 7 plus 4 plus 5. As I told you, 2 power 16, right? So that 2 power 16 is divided into 5 tag lines, 7 data lines, 4 word lines. So 5 tag lines, 7 data lines, 4 word lines. So together, if you are considering 16 bits, are you able to see one example here? Suppose we want to read or write a word at the address 357. Whose 16 bits are? Are you able to see this?
Yes, sir. Yes, sir.
We have 16 bits. Try to understand these 16 bits. So first 5 bits are for the tag field. What are the first 5 bits? 00110. Isn't it? 00110. What is the value of 00110? What is the value of 00110? Binary.
Sir, I guess your slide didn't change. It is an associative mapping only.
Which where? Are you able to see the screen direct mapping?
No, sir,
it is an
it is
associative
associative mapping.
Still.
Yes, sir.
Wait. Now? Now is it
Yes, sir.
visible?
Now we can see.
Like memory mapping lines to cache lines.
Yes, sir.
Explaining
Yes,
this.
sir.
So just I'll say. So the one which I am using is here like this. Suppose the cache has 2 power 7, that is 128. Are you able to see now?
Yes, sir.
2 power 7 is equals to 128 lines we have, and as I told you, 2 power 4 is equals to 16 words we are using, and the entire memory is having 16-bit address, so which can range from the 65536. I am calling it as a 64 kilobytes. Okay, that words we are having, and the cache memory I am telling 0 to 128, 127. So total 128 lines are there in cache memory, and the memory lines are ranging from 64k. So that means 0 to 65535. So here you will have the entire thing, memory lines and the cache lines. So here I am talking about the direct mapping. So I told you, whenever you are using the main memory and the cache memory, if you want to map directly, main memory will be considered as a J and the cache memory will be considered as a I. So we are going to map I mod J. That means, for example, second bit, location from the memory line and the second location from the cache line. If you are taking 2 mod 2, that means it will give 2 mod 2. So what is the value you will get? Modulo division. 2 mod 2. So what value you will get? You know modulo division? If it is a 2 by 2, then you will get 1. And if you 2 mod 2, what you will get? Anyone is there? What the value you will get if you do 2 by 2? Or else if you are doing 2 by 2.
0, sir. 0. You'll get 0.
Yes, that will be mapped to the cache line 0. Okay, so to identify which line we are going to move the data. So that purpose we are making use of the direct mapping. So simply 2 power 16 is 64k. So 16 lines I am using. These 16 lines are divided into 5 lines for tag, 5 lines for tag, 7 lines for the data, and the 4 lines for the word. Okay, so the division is there in the down direct mapping, you can see. Fine. So here 5 taglines I am telling. So word is of 16-bit length, you can see. Okay, so are you able to see 357A? For example, suppose if you want to read or write any word. So 357A, whose 16 bits are like this. We have some number. Fine. First 5 bits I am talking about. 00110. So the equivalent binary value for this is 6. Okay. So this first 5 digits represents the tag value. And next 7 digits. So after 00110, we have 1010 and 111. Okay, 1010, 111. So this is used for representing the line field. So if you calculate decimal value for this, you will get 87. Okay, and the last 4 digits, that is 1010, that is used for representing the word. Okay, so the 1010 binary value in decimal is 10. So we have tag field 6 and the line field 87 and word field is 10. So in that way we divided. Did you understand? Tag is 6, line is 87, okay, and word is 10. Are you able to understand?
Yes, sir.
Yes, sir.
Okay, so now we have these values. For example, this value, where you have this value is there in the main memory. This value is there in the main memory. And if you want to find if line 87 in the cache has a same tag, okay, if the line 87 in the cache has the same tag, that means the tag value is 6. Okay, then memory address 357 is in the cache memory. That it will tell. Mapping is done in that way. If the line 87, what is line 87? Line number 87 is there in the cache memory with the same tag value. That means the tag value is 6. Okay, and at that 6th position, the word is stored 357. The memory address is 357. If you are able to identify this, we can say it is a data found in the cache memory. That means hit, successfully hit. If this is not there in the cache memory, then we can say there is no data found in the cache memory, and go to the main memory and get the data from the same location and copy into the cache memory. So whatever the data is there at 87 location in the main memory, that will be copied into the cache memory. Okay, why I am calling it as a direct? Because cache memory we are looking into 87 line, and main memory, if it is there, then we are calling it as a found, data found. If it is not there, from same location from the main memory, directly we are copying whatever data is available, we are getting into the cache memory. That's what we are calling it as a direct map. whatever it is there, you can see 87 will have some value which is equivalent to 855, but that is nowhere related to us. Okay, and we are copying into the cache memory, and then the processor will execute it. So the line number 87 value required for executing the program at that time. So the processor is checking it in the cache memory, and it is there, then successfully retrieve. And if it is not there, same data whatever available at the main memory, it will take and it will copy into the cache memory, and it will execute the program. So this kind of mapping procedure is called as a direct mapping procedure. Okay, this kind of mapping, entire thing is divided into form of 16 bits, 5 for tag, 7 for line, and 4 for word. Okay, I think you will not face any difficulty in this. Why? Because if you go through this content once, you will understand clearly. So just like I am trying to explain the concept. Okay, so if you go through this content, you will understand clearly, and all the concept is explained with the help of the same example. No need of getting confusion, and all the concept is explained with the same example. So uh, did you understand? So what is the size of the, how many bits we are using here? How many bits we are using?
16.
16.
Yeah, 16 bits we are using. You know how to calculate the decimal value when that is in a binary number, isn't it?
Yes, sir. Yes, sir.
Okay, then what we have done, 87 line number we have searched in the cache memory. There is no 357, so we are going into the main memory, and we are getting it from the main memory that is already there, 855. So we are getting and we are placing into the main memory, into the cache memory. Okay, if it is found successfully, no issues, it can take and it will execute. And how we are doing the same thing in associate mapping? So the associate mapping again takes 16 bits, and here we are dividing the 16 bits into 12 and 4 bits. So 12 bits are for tag and 4 bits are for word. So all the time your processor is following the 4-bit word. Okay, entire mapping process will have the 4-bit word, and remaining we are dividing into sometimes tag, sometimes line, sometimes field, sometimes index. Okay, different things we will have. But in the associative mapping, I am taking it as a tag with 12, word with 4. Okay, so again take the same example, 357. Okay, if you have 2 power 12, so if you have 2 power 12 for example, so the 2 power 12 is almost equivalent to 4096 memory lines. That means 0 to 4095. Okay, so these are the memory lines which are available, and the word length is 4. Directly we are taking straight away, word length is 4. And how you will calculate this? Suppose I want to search the word 357 which is there in the cache memory. So the 16 bits data, whatever I explained in the previously, that data only I am taking. Okay, so here the tag is used for indicating 12, right? 12 bits, and first 12 bits you take and convert it into the decimal. So if you convert it into the decimal, the tag value will be around 855. The tag value will be around 855, and obviously we know last 4 digits 1010. So the decimal equivalent value for this is 10. Okay, the decimal equivalent value for this is 10. So now we are searching. What we are searching here? Again we are going to find. Okay, so we are going to find some information from the cache memory. So here see, 357 and 6 bits are divided into like this. Don't get confused. The 357 value only I am taking into the binary representation. The 357 value are divided into binary information. Okay, I am not taking any new value here. I am converting that 357 into 16 bits representation, and that 16 bit representation I am taking 12 into the tag and 10 last 4 digits into the word. Okay, so now the actual procedure starts. So what we will do, we will search the 855 is there in the cache memory or not. Okay, if it is there in the cache memory, then we will say it is a hit, and successfully we will take the data from the cache memory. So if it is not there in the cache memory, again we will go to the main memory, and from there we will fetch the data and we'll keep it in the cache memory. So same 855 location only we will take the data and we'll keep it in the cache memory. So this is the way you will do in the associative mapping. You can ask me what is the difference in between these two. The difference is in terms of the bits, how we are dividing. Okay, how we are dividing the bits. Here tag field is 12 and the word is 4. Okay, and next one is, am I clear? Associative mapping.
Yes, sir.
Yes, sir.
And next one is set associative mapping. So name itself is indicating set. Set means group of. Okay, so group of 2. Okay, we are making it as a group of 2 or more than 2, like we are calling it as a set. Okay, so here the entire cache is divided into sets. Okay, entire cache is divided into sets. So here we will have the tag field, and how many sets we can do. So that will be depending on the number of lines which are available in the cache memory. Okay, the number of lines which are available in the cache memory. For example, if I am taking 64-bit 64K cache memory. Okay, so the 64 is like represented in the 2 power 6. Fine. So 2 power 5 will be the 32 and 2 power 6 will be the 64. So this 6 will be considered as a set value. This 6 will be considered as a set value. So the set value is of 6. And again we are making use of tags in this. Tag is also will having the 6 tag values we are taking and 6 set values. Okay, that means same 2 power 6 different memory lines are there in the cache memory, and 2 power 6 set values are also there in the cache memory. So sets are same and tags are same. Okay, sets are 6 and tags are 6. Are you clear? Sets are 6 and tags are 6, ranging from 0 to 63. So ranging from 0 to 63. That's what here we have the representation 0 to 63. Okay, are you able to see set associative mapping? Some arrows are there, dark arrows. So 0 to 63. These are the set values. Double you will take. 0 will have to, 1 will have to, like that. 2 sets we are doing as it is 2 power 6. Okay, 0 1 0 1 0 1 like that you will have. So it is a set. 2 you will take. So that means it is doubling the things, isn't it? It is doubling the things. So 0 will have 2. 0 and 1 will have one common set, that is a 0. Fine. So from this we are taking 6. Again same example 357 I am using. Okay, this 357 first 6 bits are for tag and next 6 bits are for set and next 4 bits are for representing the word. So if you calculate first 6 bits, tag value is a 13 and together you can make 23 sets. So the tag value is 13 and sets, the possible way you can identify in that cache memory is maximum 23 sets you can do for this number. For this 357, maximum you can do 23. If you are taking different number, it will vary again. Okay, it is not fixed one. Suppose if I am taking 400, again the 400 you will convert into binary. Then tag value will change and set value will change. Okay, it is not fixed all the time. Based on the location, whatever we are searching, so it will vary. Am I clear? I am taking for 357. Is it clear?
Yes, sir. It's clear.
Okay, so now we have tag value 13 and set value 23. And word, obviously I told last four digits we are assigning exclusively for the word. So that value will be the 10. Okay, these all are represented in the form of the decimal. Now we need to search tags in cache memory. So 13 tag is there in the cache memory and 13 tag is there in the main memory. Okay, so same 13 tag in the cache memory. 2 tags in cache set 23 to see if either one matches tag 13. We need to search that tag 13 in cache memory and tag 13 in the main memory. If these two are getting matched, then we can say that is a hit. Okay, these two are matched. What it will match? The word in that cache memory should match. Then we are telling it as a hit. If it is not matching, okay, then these two values will be replaced from the main memory. Then these two values will be replaced from the main memory. Whatever the value is there in the main memory, so that will be replaced. So searching the tag 13 value in the cache memory with the two values, because it is a set. So 0 location is having the two values 13 13. 13 13 it will have. Like if you take 1, then 1 1 it will have. If you take 2, then 2 2 it will have. Double value it will have. The cache will have the double value. So it should match the two things in the either any of the thing we can store. Either if it is matching in the first one or the second one in the two sets, then we can say it as a catchy hit. Why we are using this kind of approach in the two locations? So if you want to store the different values with the same name or different values with the same tag value, so in that case we'll go with the this kind of approach. For example, a programming language you have taken, so that it may be either C, it may be either C++, either it may be Java. So it will be comes under the programming language. So what I am telling, I am storing under programming language C and C++. So if any topic is there like subroutines we will have in the C and C++. So which subroutine you want to check, whether you want to check with C subroutine or C++ subroutine. Now I want to check with the subroutine of C. Okay, then it will go to the first one. It will go to the first one and it will tell hit. So which will save a lot of time. Which will save a lot of time. So same name with the multiple locations. Okay, so that's the advantage with the set associative mapping. Okay, so once you go through this link, so I'll share the links after completion of the class. So if you go through this link, if you have any queries, like you can ask me. Okay, so it is drafted clearly, and if you go through it, you can understand. Fine. So these are the three important mapping techniques. So which are most important concepts from the unit 3. These are the most important concepts from the unit 3. So direct and set associative and the associative mapping. Okay.